Hello, my name is Doug Yeager, and I want to thank you for taking the time to join us today for our Potting and Encapsulation webinar, Application Problems, Practical Solutions. The potting and encapsulation application is a widely used application that crosses products and industries. We hope our conversation today proves to be of value to you and your company. Exact Dispensing is a company that designs and builds dispensing systems for potting and encapsulation applications. We are focused on the meter mix dispense of two-part reactive chemistry resins. Exact is part of the TASI group of companies and is located on the beautiful coast of Maine. Our approach to the business is to take a practical, solutions-oriented view with the simple goal of helping you solve your problems in the most effective way possible. Based upon years of experience, we find it is needed to partner with you so we fully understand your needs so we can get to the root cause issues that lead to lasting solutions. Today is a first conversation that we hope is followed by a direct dialogue with you. Our success today depends upon whether or not we can meet these goals. First, we need to identify if a problem exists, and if so, what are the likely root causes of the problem. Are the root causes starting on the resin side of the problem, or are there other factors that exist? When we know or think we know the root cause, then we need to look with you at practical solutions that can be economically implemented. The people we have involved today are myself and Chris Connery. We are both equipment veterans who can bring a lot of practical ideas to the table. I am the general manager of Exact, and Chris is our director of system solutions. When we combined our experiences with you in a partnership approach to problem solving, we believe a lot of good things can and will happen. Though it is difficult for us to listen to you in this webinar approach, listening to you is in fact what we want to do and are trying to do in this format. We hope you don't find our thoughts too simple, but I must admit that many times the most simple solution leads to the best and most profitable solution. There are literally hundreds of thousands of products that are potted or encapsulated. These products are used in almost everything we use or build. Therefore, we think what we are now going to talk about is important to virtually every industry, including automotive, energy and lighting, machine builders, pump and motor manufacturers, and hundreds of others. As step one in our efforts today, we must learn how to identify common problems and possible root cause issues. A practical place to start is by looking at the resin, as this is what gives you the solution you need for your product. Is the resin, when it is dispensed and cured, still completely uncured, like the example shown on the right? If the cured material is striated, not uniform, this indicates another problem. Are you wasting material and time by working with unworkable processes such as the cup and stick meter mix method? How important is material cost on your component cost? And are you exposing your operators and your factory to any unsafe operating conditions? These are all important questions to ask and to get answered. Does your finished part look like the picture shown? Is it filled with voids in the cured resin? What kinds of field failures are you experiencing? Is the surface finish smooth and continuous, or is it rough and pitted? How often do you overfill or underfill in production? To help your process, a clear understanding of these issues is critical. There are a range of problems you may be aware of that are operational in nature. How dependent on the operator is your success? As an example, are you leaving it up to the operator to eyeball a solution that could effectively be volumetrically metered? Have you ever calculated what it costs to consistently overfill when underfilling at 90%, as an example, may deliver quality parts? Increasing production rates is a great way to improve profitability. Are you operator dependent in this area? If you have been doing prototype development using a manual meter mix approach, how can you scale up to production rates? Is the cost of labor a key factor influencing your success? After identifying your list of problems, we must work with you to determine if the resin materials are at issue or something else. We suggest it is always good to start with the basics. As equipment people, we only need a basic understanding of the chemistry, which we will review now. To start, potting materials are not adhesives, and they typically have lower durometer characteristics. We know that thickness has an impact on how your part responds to moisture. Is the material thick enough? And what if you have underfilled the part? Does it automatically lead to failure? As equipment people, we like forgiving and friendly resins like urethanes and epoxies. But when the features of these materials don't meet your needs, we need to be able to handle more difficult resins such as silicone. The resins you select are not our area of expertise. What we do know, however, is that if you want a more rigid final part, an epoxy may be best. If having a part that is soft and flexible, urethane may be a better solution. If higher temperatures are being exposed to your part, then silicone is more likely the best selection. After you have selected the right resin, the thing we are interested in is the viscosity of the mixed material. To properly encapsulate the resin must have appropriate flow, but not so thin that it leaks out of the part. One way to increase flowability is by adding heat. Heat reduces viscosity and can improve consistency of viscosity, but it also reduces pot life. Reduced pot life can be good, more and faster production, or bad. Material cures before you get it into its correct place on your part. There are a few viscosity rules for you to have in mind when this subject is discussed. A simple one is that when you increase viscosity by 2 times, it becomes twice as thick. This may sound simple-minded, but is critical when you consider that by moving from 1,000 centipoise to 2,000 centipoise material, the flow rate through a piece of equipment will be reduced by half when all other inputs remain the same. You should also consider the impact this change may have on the flow of resin under and around components within your part. We suggest the goal is to have the lowest viscosity material possible while still meeting your other product needs, like saturation rates within your part. As you can see in these videos, as viscosity increases while the material is going through its pot life, the ability of the resin to flow changes, which impacts the quality of the final part. There are a few equipment solutions you might want to consider as you contemplate viscosity. First, working with higher viscosity resins requires you to use pressure feed supplies to your meter mix equipment. If you do not provide enough pressure, systems tend to suck air, which results in off-ratio metering. Adding heat to your system is one way to help manage viscosity. You can do it at the component level, or even better yet, implement a half or a full heated system, such as those depicted on this slide, that puts all the metering elements, including the resins, in a heated chamber that is set to the operating temperature you need and want. When you talk about adhesion and rigidity, the impact on any equipment solution is minor, if any. What you need to keep in mind is that you may want some adhesion, but not too much. You want rigidity, but only that which is in line with the needs of your final product. Now, when it comes to the need for fillers, we are concerned as equipment suppliers. Fillers are used for a few reasons, including better heat dissipation, added mechanical strength, and to reduce the cost of the resin. No matter what the reason, adding filler adds complexity of the equipment's solutions due to increased abrasion and the knowledge that all fillers eventually settle out of solution. This is one of the reasons why we use large, slow-moving cylinders with enchromatic dispense options. Fewer cycles per gallon results in longer life. If the filler is not properly dispersed, the properties of the cured part will be impacted. The key issues we live with are that fillers lead to increased abrasion, which affects equipment life. When the fillers settle, you must implement a protocol that keeps them in suspension. Typically, investment in recirculation and agitation are needed. When you go to recirculation, you are moving many more gallons of material than you are actually dispensing. You must know the settlement rates to know how much recirculation is needed and how often you circulate to maintain production. All supply tanks must be agitated, but at a rate that does not introduce air into the liquid. The metering systems we like to use at Exact when the material is heavily filled are single acting designs such as that pictured on the bottom of this slide. They allow us to purge the meters when not in use. It is also critically important to start a repair before breakdown protocol that allows you to keep up production and maintain quality. Pot life is another material feature that has a big impact on your application solution. Pot life is basically the amount of time a mixed material remains workable in your product or process. You need to remember that as the pot life time is used, the material is constantly changing viscosity. It is therefore very difficult to use hand mixing processes when the pot life is fast. When the material gets thick, it is harder to get the air out before it cures. This is one of the reasons we have developed the new Patriot entry-level meter mix machine for users who just can't get along anymore with hand mixing types of solutions. There are a few other things to consider relative to pot life. As an example, longer pot life results in better flow out of the mixed material. There are fewer equipment issues and typically less material waste. But production may be slowed because the material cure takes longer. The shorter the pot life, the more likely your equipment solution will require an AutoShot Pot Life feature. The picture you see on this slide shows a hole in the production table that will hold the automatic dispense valve, so when the Pot Life AutoShot goes off, the material is purged into a waste container and not onto the floor. It is very important to use air-free resins in your potting process. What does it mean to be air-free? It is simple in that you don't want bubbles in either the resins as you try to meter them in an accurate ratio, or have air entrapped in your cured part. It is critical to take steps to not introduce air into the resin with such things as drum rollers, and also to take the air out of the resins before you use them by a degassing process. There are a number of simple design considerations that can help preempt application problems. We will do a quick review of some of these now. Know your bubble basics. Bubble rise in a liquid. So, to give your resins a chance to let the air rise to the surface. Bubbles under pressure get smaller, but they do not disappear. See the video as the pressure goes from 30 psi to 60 psi. The bubble changes size. It is very important, no matter whose meter mix equipment you are using, to get the air out of the system. We use a simple bleed process that's pictured here in the second video on this slide. Bubbles are more than just a problem with metering accuracy. The presence of bubbles can cause your parts to fail due to a wide range of issues. On the way to make sure you don't have bubbles for critical processes, or one way to make sure you don't have bubbles for critical processes is to dispense under vacuum. You also need to keep in mind when you are designing your parts to avoid tight gaps that make bubble movement difficult. It is always best to start with a bubble-free resin. If you do start with bubble-free materials, then you must also use processes that do not have the potential to add bubbles or air to the materials when they are processed. There are some meter mix systems that, quote, fill their chambers by creating vacuum in the metering chamber that is then violently filled with resin when the rod is removed from the chamber. There may be situations where this is not a problem, but it can typically lead to changeover off ratio conditions that must be masked by the mixer. You should also avoid splashing of the dispensed resin. This video shows how keeping the dispense point within half of the stream diameter minimizes splash bubbles. The design of your components can also help a lot to prevent potting problems. We encourage you to evaluate bottom-up filling options that allow resin to enter the part from the bottom and exhaust air out the top. We have pictured not only bottom feed, but a tilt dispense approach that eases the evacuation of air from the part. These kinds of design should be considered. We also, periodically, have found that by dispensing resins onto a heated part, boundary issues between the resin and your part are influenced, allowing better fill results. When you design your production processes, you should develop resin distribution strategies such as those discussed here. First, consider if you are moving the part to the dispenser or if you are moving the dispense tip to the part. This will help you decide how to best position the dispensed resin, such as into a corner, wall, or into the center of a part. We typically suggest 1/3 in from the edge of the part. As you can also see from the video, the use of splitters can be effective. A splitter with equal resistance features will dispense a split flow in an equal way. When the split resistance is not the same, the flow is not the same. Volumetric metered shots are also a very good idea, especially when you tied in split resistance. If you know how much material is needed to give you good potting results, use of your exact inchrematic dispense option to deliver only the required amount of material is a good idea. There are times when you should dispense in a vacuum. By dispensing in a vacuum, the liquid quickly and easily flows around the part as there is no air to stop its flow. There are a lot of dispense in vacuum equipment options available, and you can see some of those on the slide in front of you. You can also consider vacuum after the dispense, though this can be inefficient and cumbersome. It does work, however, and will quickly remove bubbles from your part. This can be critical, as an example, if micro bubbles are a concern. Sometimes you may put parts under vacuum before using them to get rid of unwanted vapors, such as solvents that might be in the components of the part. So, how do you troubleshoot your system when you determine you have a problem? We first suggest you must determine if the meter mix system is metering on ratio or not. Start by taking physical measurements of individual resin and catalyst stream after metering but before mixing. If the mix ratio is wrong, such as that shown in the video, the first thing to look at is the presence of air bubbles in the materials. If you have an adjustable ratio machine, make sure no one has adjusted it or that it has come loose and self-adjusted into an off ratio condition. Exact dispensing systems are fixed ratio designs designed for your material and your specific process. Air-free materials are key to successful meter mix of 2K materials. The videos on the right side of this slide are dramatic, showing how air in the original resin can be drawn out of the resin with vacuum, but also show how much air may be in the resin in the drum. Vacuum degas before trying to meter is a great rule to follow. The design of the meter mix dispense equipment you specify has a big impact on the likelihood that air entrapment will become a production issue. We are absolutely convinced that you should always use pressure feed to supply your meter mix system. When you pressure feed an MMD or a meter mix dispense system from Exact, we guarantee we will never put air into your material. We also have a nearly equal pressure design in our double acting systems that makes air entrapment virtually impossible. Unless you run out of material. If you allow your supply containers to go low or empty, you are inviting a problem. We like to use cascade drum feed as an example, or large toggled tank feed with low-level controls to assure these problems never occur. There are many systems on the market that depend on, quote, check valves to control the meter mix function. As you can see from the video, the closing of check valves is highly impacted by the viscosity of the fluid. The thin valve always closes before the thick valve. At Exact, you can see in the video, we use what is referred to as an LDV, linked diverter valve. This assures simultaneous valving of the A and B components and is not viscosity sensitive. A fully functioning system should be designed keeping all of the items we have discussed in mind. Systems that are designed for the potting and encapsulation process must address key issues that may not be present in systems designed for other 2K processes, such as those used by contractors or other who have lower standards. The solutions we have discussed here today are proven around the world. It is now with great pleasure I'm going to turn over this session to Chris, who will answer for you some of the questions being submitted. Chris, the floor is now yours.
Thanks, Doug. Let's see what we have for questions. Okay, here's a question that's come in. I see variations in final material consistency from morning to the afternoon. I think that's probably referring to, viscosity and such. So let's see what that is. Many materials have a lower viscosity in the hot afternoon. And I would say that if your metering system is sensitive to these sorts of variations, the ratio can be erratic and the cured properties will be different. Your system may need adjustment through the day, but an Exact system does not need tweaking throughout the day to hold the proper ratio. We use linked diverter valving and positive pressure supply to hold those ratio problems in check. Is it okay to feed materials from a pressurized feed tank with 80 psi of air or nitrogen? Liquid, all liquids absorb gas. Some, like silicones, absorb air faster than others. This is not a serious problem with a single part dispenser, but in the two-part dispensing business, it's a big deal. Variations in compressibility between the A and the B components will add risk to the on-ratio delivery. We avoid it in our machinery because we use supply pumps to pressure feed our systems, and we don't use pressurized tanks if we can avoid it at all. And it's mostly because the air is inside the liquid, it's entrapped, and it adds compression, and it comes and goes. I see hazing or fog on my finished part from time to time. Do you have any suggestions that may help? Well, some amines blush in epoxy systems. That's relatively common. So if it's an epoxy system, that's typically no big deal. But sometimes the problem is linked to the ambient moisture, like during a rainy day or working in a humid environment. it provides moisture that may be reacting with material before it cures, and it's more common with urethanes, some epoxies, of course. I guess there's a typical fix. The typical fix for that moisture problem is that you would just heat the part, and that'll rise the dew point to drive off the moisture that's affecting the cure of your part. Your formulator is going to have some specific knowledge to contribute there. This question, all right, we'll skip that one for now. Let's try another one here. Oh, this one's pretty straightforward. Can you help us dispense on a tray of parts automatically? Yeah, sure we can. We can help with the first tray design and also the production quantity build as you wish. We have expertise in-house to do that first tray design that we can contribute. And we have CNC machinery in-house to build production quantities if you'd like to have our help there. We can also provide an XY to work, move the dispense tip or move the part. And we're also happy to work with automation houses to deliver the digital preset shots to the appropriate locations within your part and multiple parts on a tray. The tray can also be fed with a conveyor. So the best thing on that is just to talk about it, to understand what it is you'd like to have done, and we'll see what makes sense. All right, this one it's a little more complex. Let's see if we can understand what we're driving at. I have air bubbles in my final potted urethane part, but it's not all the time. I use a nitrogen blanket on the isocyanate tank supply side, and it's basically, am I doing something wrong? So this is a urethane, so the fundamental piece is probably already understood that isocyanates are in urethane liquids, and isocyanates react with water to form abrasive crystals and CO2 gas. Typically the water comes from air that sits over the material in the supply tank, and you can add a few drops of water to any uncured urethane sample and see what I'm talking about. It basically foams up as it's making that CO2 gas. But to get really back to that question, you're blanketing the isocyanate side, and that's great, and that's where most of the problems come, but nitrogen is heavier than air, and it forms that barrier to protect the material from the moist air above it. Unfortunately, we find some folks that don't bother to put nitrogen on the polyol side, and you need to add nitrogen on both materials. If you don't, the wet polyol, when the wet polyol contacts the isocyanate, it still starts the same CO2 producing reaction, and it makes bubbles in your part. So not only is the moisture a problem on the isocyanate side, but it's also a problem if you bring in the moisture from the polyol. The polyol is usually pretty benign. You wouldn't know that there was a problem there until you combined it with the isocyanate. So the other, I guess this has another piece that's the other possibility, I suppose, is that the crusty isocyanate crystal buildup may have ripped out the seals in a suction style metering system, and the air is being sipped in during a recharge. It doesn't take very much on a suction side to sip in air. If the seals are worn at all, the air can kind of seep its way into that suction side, and then cause an off ratio as it gets into the system. Our systems are positive pressure inlet, so the seals are all that are responsible for the metering are all positive pressure fed. So the leakage for us leaks outward and doesn't really affect the ratio. So the bottom line is that moisture is a problem, and it's probably what is causing this problem. Yeah, this one's a good question. Are dynamic mixers a good option? Yeah, they are. They're a great option, but they add expense and some maintenance as well. The dynamic mixers can help mask upstream ratio delivery problems. So if your machine is making off-ratio materials, it'll help out there. But for us, we rarely need to use a dynamic mixer because we have few ratio delivery irregularities. The inline metering systems with link diverter valves deliver the two materials on ratio over a wide range of material fluctuations. What we do find is that the dynamic mixers help if it's a real fussy, hard to mix material, and then for sure we'll put it on. So we have dynamic mixers. Most of the time the inexpensive plastic static mixers are fine, and that's just our experience that the dynamic mixers are not needed. How big a shot can your system deliver in one stroke? Well, we have a lot of different systems, but the large series system is our 9450 single acting inline metering systems. And they hold 945 cc's from the 3.5 inch bore 6-inch stroke major material cylinder. The minor cylinder is machined here in Maine to produce the parts by volume ratio of that material that you want to use. Typically the inline combination of the two cylinders ends up around 1500 cc's per stroke. It's kind of like 1.5 quarts of material. So that means that for us there's 150 10 cc shots that we can take incrementally for a given stroke, and then just go through one recharge cycle. Our machines are not the single stroke pump design. The shot size itself can be much larger than the 1.5 liters. It can go on forever. It doesn't really matter to us as long as you have sufficient supply. We'll just have a few recharges every 1.5 liters. And we can initiate the recharge at any time. So if you finish a tray of parts, it's easy for us to do that. Just push the button and it'll recharge. Is it easy to swap one formulation for another? Well, sure, it can be. If it's a similar chemistry swap, we would suggest chasing one out with the other. One side, of the A with the A, and the other with the B with the E, chasing the two out. We're not chemists, but we would always suggest that you combine the old A1 material with the new A2 material, and then combine the old B1 material with the new B2 material in separate cups, and then just set them on your desk. If the separate components are still flowable in the morning, then the risk of turning your machine into a brick is kind of a bit lower, and your life will be easier when you make that clean and swap event. But the bottom line is that it's just not a big deal at all to give us a call, and that's what we would prefer, is just call in, and we'll offer some advice, and we'll update our database with your intentions, so we'll know what you've got in your machine for the future, and be able to help further on down the line. And if you need to change the ratio on our system, that's not hard for us. You unbolt one cylinder and put the other one in. It takes less than an hour to do that minor component cylinder swap. Other machines do it other ways. Some have different linkages and arms that move to adjust the cylinder stroke. In our case, it's just a simple cylinder swap. But the best thing is just to give us a call. If there are viscosity differences, we may be able to advise about flow rates and things like that. This one's, can I put an uncured part into a pressurized tank to help shrink entrapped bubbles? So I think what they're driving at is kind of like the older style of encapsulating coils and such, where you would put the wet component in a pressurized tank and put it under pressure, and PV equals PV, so the void volume would be reduced by the pressure, and the pressurized liquid will now go into those areas. The problem that we see, we really don't see this done very often, but the typical problem is that, it uses up a lot of expensive pressure tanks. These days, it's more common to vacuum the part first and then add the potting while it's under vacuum, and then release the vacuum to the ambient pressure after it's all wet. So that causes the liquid to be forced into those same voids due to the 10 to 14 psi increase from the vacuum level. And when you're releasing the vacuum, the part tray comes out of the vacuum chamber, and you can sit them out in the open for a cure over 24 hours or whatever. And it doesn't use up expensive hardware just to extend the cure cycle. But yeah, the pressure obviously works both ways. You can add pressure to reduce the void, or you can use the vacuum to pull the air out and then let the pressure go back to push the liquid in. All right, I'll read it. I don't have a question. I just wanted to extend my appreciation to you guys for the helpful support you've extended us over the past decade or so. Yeah, thanks. We have a great, courteous, experienced crew here in Maine. Our service database provides quick access to specific information on every metering system. Our employees throughout the U.S. and around the world also have access. And, UPS, Red, and email connects us all. So I appreciate the comment. We'll come back to this one later. But this one's kind of in line with the other question. When vacuuming, let's see here. When vacuum conditioning my supply tanks, how do I know it's ready? Well, let's see. That kind of goes with we don't know what the level would be that you need, but from a housekeeping standpoint, it's relatively straightforward. Most of the exact supply tanks have windows in the lid to look through. You turn the vacuum on and the bubbles will start in the liquid and foam up, and when the bubbling stops, you're done. The liquid is pretty well rock hard. If you don't have windows, you can learn the characteristics of the material. May not be exact, but it's pretty close. You turn the vacuum on to say 24 inches and let the material rise for 10 minutes. Then release the vacuum and let the level drop. Then you have to open up the lid and just look down the wet sidewall, and it'll show the height of the material as it's foamed. It's kind of like a water line there, so that the liquid, while it's foaming, comes up the sidewall of the tank and keeps it wet. So you can now see the height of the foam that you've just made with the vacuum for 10 minutes under 24 inches. And you just clean off a vertical patch on the sidewall of the liquid foam line with a rag until the tank is clean, so you can see the side. And then you just repeat the process. Go another 24 inches for another 10 minutes or so, and keep on doing it. And eventually, at some point, the foaming won't foam anymore. There won't be any foaming, I should say. And you won't see any residual foam waterline or staining on the sidewall of the tank. And then adding up the total time for each one of those cycles will give you an idea how long it takes. And then go ahead and do it the next time with another batch of material and see that it's about the same time. It's a nice way to do it when you don't have the vacuum window capability. Oh yeah, this was what we were talking about during the earlier part of the presentation. This is in reference to the presentation we just did. It says, what is that dispense from the corner 1/3 of the way out comment about? I'd say, try it. So typically the flowability of the material through the part is slower than the dispense flow rate. So let's think about that for a second. So that the flow rate that we're providing out of our machinery through the static mixer is providing air-free material to your part. But the flowability of the material as it's cascading down the part is really a separate event. It flows with the viscosity that is and the obstructions and gaps. So every part has a special flow path clearances and characteristics. We don't know what they are right off the get-go, but certainly easy to watch. So if you dispense at the top of the board at the very corner, and very corner, which is what you might think, the material may end up overflowing the corner walls in a short amount of time. So the very corner usually isn't the way it ends up. We would normally try and see that a tilted dry assembly, a few degrees, let's say 5 or so degrees on one corner, and positioning the tip of the dispenser below the highest corner an inch or so, or the third of the way towards the center, and then letting the liquid flow, and that typically allows room for the material to naturally flow back into that upward corner and around the perimeter edge of the board, and then it goes underneath the board and inward like a wave on the beach, just pushing the air ahead without any entrapment. And the other section of the liquid just flows over the top of the board all the way down towards the bottom. So you have two things going on. That 1/3 location is good because some liquid will travel back up and then flow in around the top edges of the board, and then in underneath the board all the way down. And then the upper part of that board still gets coated just like you're asking for it to do. And if you try the center, you might get lucky, but there's a risk that the materials will fall over all 4 edges and then flow underneath the board and meet right up in the center underneath the board and trap a bubble in the very center. And these are things you all have to just try out, and we're happy to help out there. And the best thing to do is just to get the best prototype assembly that you can find, and either pour just the resin or the mixture over various locations until you learn what the best flowability is and what the flow rate might be. And then you can start thinking about the actual flow rate the machine needs to keep up with to exceed that goal. It doesn't make any sense to have a machine that'll deliver 20 cc's a second if your part won't accept it faster than 5 cc's a second. There's another, just a simple comment. I love coming to see you guys in Maine for machine acceptance, and appreciate all the help you gave us with our new parts to be potted. I know these guys. What they're referring to is, we really do love helping to make these new product launches go smooth for our customers. We're not miracle workers or anything like that, but we've got years of hands-on experience, and we have a full use of a nicely equipped shop to use while those components and design engineers are in the building. And it just makes it kind of fun. So, and when when the system leaves the building here, everybody knows what they're up to, or at least has a great place to start. And that's all done at the wet test. Do you make an entry-level machine? Sure. We have a small entry-level machine we call a Patriot, and it's configured with the same exact ratio performance characteristics, but it's intended for startup production. This is a good quality machine. It's just meant for startup. And the best way to figure out if it's appropriate is just to give us a call and tell us what you're up to, and we'll go back and forth. And if it fits, it fits. Here's a good fundamental question. I'm glad that was asked. Are gear pump metering systems better than piston metered systems? I'd say that depends. Gear meter systems are fine for many unfilled materials, but typically potting materials have a filler on the major side, and the minor side is very thin like water. So the filler wears the meshing gears of a gear pump, the sides and anything that contacts the metal. And the filler settles and packs in between the gear teeth and can really ruin the pump. It's not only just the gears, it can ruin the bearings. And with the materials on the minor side being so thin, it adds to the risk of off-ratio delivery through bypass of these tight clearances in the metering pumps all around those gears, because there are no real seals in a gear pump. And if you want to just blow through a gear pump, you'll see that you can blow through it. So some liquid is going by. Our piston meters, for potting work out really well. They have replaceable seals and prevent bypass. And the piston motion on the cylinder is really slow, and it just distributes that wear over a long stroke. So it's much easier to use, or better to use, a piston machine for these filled materials, which is most of what potting is. This question's a little out of our league, but we'll read it. It's what is a reasonable temperature to heat my resin? I think your formulator is probably the first call there to offer some guidance, to establish some minimum and maximum and viscosity curves. For production, implementation of the material is usually determined by the flowability of the mixed material within your part. The idea being that if it's cold, then the material is going to flow slower in your part, and if it's hot, it's going to go faster. And if it's too hot, it may leak out, or if it's too hot, it may cure too fast. So there's a balance there that is hard to determine over the internet, of course, but the best way is to try as little heat as possible. Consistency and repeatability of the process is a lot easier with a lower temperature. It's not like a knife edge type control system. It's much easier to hold in a production environment. And most of the time we find that 80 or 100 degrees F helps to assure that the mixed material flow characteristics are what you can count on. And we rarely see over 140 degree resin temperature being used. The general idea is you don't want to cook or char the resin. We make suitable heated enclosures for the whole system. I believe there was an image or two on the original PowerPoint. The heated enclosures are good. They're good value because when you start adding up the individual heated component costs, it exceeds the price of the heated enclosure. This one's more of a specific gravity question. Let's go with that. I think that's what we're driving at here. My parts by weight ratio is quite consistent, but it's heavier on the minor side than it used to be. The parts by weight ratio is consistent, but heavier on the minor side than it used to be. So it's either heavier on the minor side or lighter on the major side, because the ratio doesn't necessarily know the difference. So I would say if this is a potting material, it's not clear that it is, but if it's a potting material, the specific gravity of the major side may be lower for this particular batch, lowering the ratio number that you calculate. That's pretty common. The formulator is still providing good cured characteristics you need. They typically have variations in filler amounts that that are allowed in their recipe anyway. And usually the TDS sheet indicates a specific gravity range acceptable from batch to batch, but they do range. So if it's lighter on this particular batch, and your ratio will be reflected a smaller number. But I guess maybe I'll add to that, if the ratio is intermittent and not more of a steady event, you should just be sure to check that the filler is not at the bottom of the tank or the drum that you're using, because you could just be pulling the lighter material off the top layer. We would normally provide all machinery with filler with a slow speed agitator to keep that material in suspension. And it's easy enough to inspect. Stick a stick down into the bottom of the tank and you can feel the filler down there. Or you can use a specific gravity cup. specific gravity cups are available from us or the scientific folks, and they'll allow you to measure your specific gravity of each batch of resin and hardener as you see fit. This one's more something simple. Yeah, it's easy. This one's easy. It says, I used to visit Maine when I was a kid. How far are you from Portland? That's easy. We're an hour up the coast on Route 1, 3 hours from Boston. Stop by anytime. We're not that far up the road. I think at this point, that's the questions that we're going to go for at this point. This has been kind of fun. Maybe not as good as the summertime on the water in Maine, but fun. And over the next few days, we'll look through some of the other questions and try to clean up my responses and answer a few more. The best way to continue the dialogue is to call us on the phone or send an email. Our current customers already know us, and they already know how we conduct business. I hope that those of you needing some fresh advice with a potting situation, they'll give us a try. Look forward to your call. Thank you very much.